Good day, students. You are welcome to another lecture of today. Today, we are going to look at a very important topic, which I can describe as a gateway into the study of chemistry and physics. That topic is what? Mass and weight. It's a gateway into the study of chemistry and physics. You can call it a physics topic, you can also call it a chemistry topic. But for somebody who really wants to understand chemistry and physics, you must understand the difference between mass and weight. In the ordinary world, the two are being used anyhow and interchangeably. And at times it makes students to get confused about which is which. So I will take out time to explain each and every one of them properly, so that we can know the difference between two of them. On most occasions in chemistry is more interested in mass, while physics is principally interested in weight, although physics also needs mass. So we must know the difference. Now, let us look at what is mass and what is weight. The amount of matter that make up an item is called its mass. This thing I'm holding is matter. This big, this whiteboard marker. This is matter. This thing I'm holding is made up of billions of particles. It's made up of billions of particles. And those billions of particles is what? Either proton. Proton is there, neutron is there, and electron is there, as I explained in the former lecture. When you accumulate these billions of particles, when you accumulate them, you get millions of atoms. When you now accumulate these millions of atoms, you now get the particular matter you are interested in. Is it iron? Is it aluminum? Is it copper? Whatever it is. So let's use this thing I'm holding on my hand as an example. This thing I'm holding on my hand, this thing I'm holding, this marker, whatever it is, we call it matter. So all this accumulation, all these billions of particles, millions of atoms, holding themselves together, they don't want to leave each other. They came together, hold it themselves, make up this matter and hold it on my hand. This is what mass is all about. And mass is same in all parts of the universe. If you take that mass, any part of this thing, it will give this, that same quantity is still that same quantity. It doesn't change. But what is weight all about? We just came to this world to meet this natural force that acts on anything. The earth, look at the earth. You remember the solar system, something like this. This is the sun at the center. Then you have other planets round. This is a planet here. Another planet that goes around the sun. Another planet here. Another planet here that goes around the sun. The earth is the third planet. This is the earth. And the earth here has its moons that goes around it. The moons. So if you take this natural, this is the earth, this is the earth. Not exactly also Africa. As the earth is here, the earth has a center of the earth. If you dig inside the ground, you cannot even reach it. You have the center of the earth, the core of the earth. Nature has it that any object within the vicinity of the earth, whether here or here, or here, or here, or here, or here, or here, the earth will try to pull it to itself, drag it here to the center, drag it here to the center, drag it here to the center. This is how it is on not only the earth, on all the planets. This is the earth. On the moon, the same thing. This is the moon. smaller than the earth. But nature also had it that way. God made it in such a way that anything within its vicinity is dragged to its center. The same nature made it that any other planet, including the Mars, the Mars is another planet that belongs to the solar system here. Anything on here around its vicinity, this planet will not allow it to go. It must drag it to that. It must come to the center. These are pull. When I say pull, that's drag it to the center. This is the center of this one. Center of this one. This one has its own center. This one has its own center. Now, this pull, with the planets, each of these planets drag matter, is referred to as what we call the force of what? Gravity. And this force of gravity varies from place to place. On Earth, anything matter around here, you drag it to the force of 9.8 Newton. Listen, I'm coming to explain. If you take some millions of this that is 1 kilogram in mass. This 1 kilogram in mass, if you take it to the earth, or this earth and measure it, it drag to the pool of 9.8 Newton. On the moon, it should drag it to 1.62 Newton. That's the drag, the pull. And on the Mars, it is 3.73 Newton. Now, how did we come about this 1 kilogram? Scientists all over the world need a measurement that does not vary. If you're a scientist in Nigeria here and you get a drug from overseas, and a scripture is telling you, measure so and so quantity of drug, mix it with so and so quantity of this, and then you get so and so drug, and that is mix so and so chemical, mix the other chemical, another chemical, then you get another chemical. Then you need a measurement that does not vary. Hence, that's why we have the mass. The mass is a measurement that does not vary. The world sometime came together and they measured a prototype of this, of a metal called platinum, iridium. It's a mixture of two metals that does not rust. They measured a certain quantity of it and call it 1 kilogram. This 1 kilogram is what we call an international prototype. It's a piece of metal kept in International Bureau of Weight and Measures in France. And this object is called International Prototype Kilogram. Its mass is 1 kilogram. This is our standard, which we normally use to measure mass all over the world. So based on this 1 kilogram of mass, we can now use it to duplicate. The standard, this is kept in France, is duplicate, it's also kept in other parts of the world. So this, we now use this thing to measure everything. For instance, if you want to get you put a knife edge here. You put this 1 kilogram. This is what? The 1 kg prototype of platinum iridium. Now, anything that balances this 1 kg, surely, by my right, surely must be 1 kg. As soon as I put some quantity of sand here, and as I put some quantity of sand here, this thing that is sitting like this now balances automatically. This sand is also what? This is the sand, or say matter, be measured. So once you measure it like this and you balance it, automatically this 1 kg here is automatically 1 kg of that matter. So this is some international standard of measurement which you normally use all over the world. Now, this prototype, as I told you, is kept in France. Scientists need to make comparisons all over the world because that's why the world came together to agree on what is 1 kilogram. If you know what is 1 kilogram, automatically you can get what is 2, 3, 4, 5 kilogram. And this 1 kilogram of mass, as I told you, was measured on Earth here. This 1 kilogram of mass was measured on Earth here. This 1 kilogram of mass was measured on Earth here. This standard 1 kilogram of mass was weighed on Earth here. And that 1 kilogram, when it was weighed on Earth here, it gave us a weight of 9.8 Newton, approximately. This is on Earth. If 1 kg on Earth measures 9.8 Newton, then something like say 5 kg, say, just we give you what? 5 over 1 times 9.8. This gives you 49 Newton. So 1 kg on Earth, 1 kg mass measured on Earth here gave us a weight of 49 Newton. The same 1 kg was taken to the what? Was taken to the moon. And when it was getting to the moon, it was also weighed. The pull 1 kg. The pull that dragged it was 1.62 Newton. Now 5 kg say, I think we need to get 5 kg in the moon. 5 over 1 times 1.62, which gave us 8.1 Newton. Now, let us see what happened. When the same 1 kg was taken to the Mars, another planet called Mars, the same 1 kg, that prototype agreed all over the world, was taken to another planet in the universe. When on getting there, that 1 kg was weighed, and the weight gave us 3.73 Newton. So suppose you have 5 kg, for instance, say, this will give you 5 over 1 times 3.73. On the mass, it will give you what? 18.65 Newton. These are the various weights we got using this 1 kg that was agreed on Earth as our standard of mass. It's taken to the Earth, see what it gave us. Take it to the moon, see what it gave us. Take it to the Mars, see what it gave us. So, how did you measure? What did you weigh? We have different types of weighing system. As standard weighing system all over the world. Can see what I'm holding on my hand? This is a weighing system. This is a weighing system here. This is a weighing system here. You can see this is weighing a bag. The bag is hung here. The weighing system, there's an arrow here to pull down. This is another method. This is another content. It's also carrying scraps of this is a motorcycle skeleton. It pulls down. This one built another company, which traders might use to measure nail. The pour nails or any iron inside it, and this the deflection will show you. These are various ways of weighing. So this weighing I'm showing you now, I'm on Earth. If I measure weigh it, if it's 1 kg, I'm weighing on Earth here. I should expect 49 Newton. That should be the weight. Now, if that 1 kg mass, I take it to the moon, it will give me 8.1 Newton. If that 1 kg mass, I take it to the Mars, it will give me 18.65 Newton. As I'm going to the moon, on Earth here on Mars, I'm carrying these machines, this thing you are seeing here. This is what we call a spring balance. It comes in different forms. but they give you the same weight. Depending on how you, they have the same mass, but they give you different weights, depending on how you are. If you are on Earth here, it will give you a different thing. If you are on Mars here, it will give you a different thing. And if you are in the moon, it will give you a different thing. Now, based on all this calculations we have done there now, we came to this important formula, one of the most important formula on Earth called W. From all these things I've done here, somebody of all these things will give you this W is equals mg. This W is equals mg is a very important formula in mathematics, in physics, in mechanics. It emanates from Newton's second law. It emanates from Newton's second law. Force is equal to mass times what? Acceleration. We will come to that. This is a special form of this formula. What is telling us about? That the more you apply force on something, the more the acceleration. That is very clear. If I say, look at this and hold my hand, look at it here. How sharp it will move is the amount of force I apply. And it's force. It has moved. This is force, it has moved. This is force, it has moved. All these are forces. So the more the force, the more the acceleration. So that's why we say force and acceleration are directly proportional to each other. Directly proportional to each other. What does it mean? The more the force, the more the what? Acceleration. As this one is increasing, the is also increasing. If you reduce the force, the acceleration will also what? Reduce. So if you introduce constant to give it a mathematical meaning so that you can solve it mathematically, you now introduce equal to here. Remove proportionality, produce equal to. Now force now becomes what enables us to produce equal to is we have to bring in the constant, which is the what? The mass. Mass and acceleration. When we study Newton's law of motion, we get more about this. So what I'm just trying to say is that this formula, W equals mg, is a special form of this formula. It originates from this formula. And this is one of the most important formula in physics, in mechanics. This formula, force equal to mass acceleration, which W equals mg originated from. Now, still on mass, weight, we want to freely get the difference between these two. I want to understand properly because, as I told you on X side, we used anyhow, and students get confused. Some of the study chemistry and physics don't know which is math. We don't know, so we don't use it the way other people use it on Earth, in the marketplace, and the traders use it. Now, let us look at the diagram of the Earth. The Earth, we are told, is spherical, not a perfect sphere. At times it goes like this. Some places it has mountains that go like this. It come like this, goes inside valleys, come like this, come like this. Fine. We are on the surface of the Earth, human beings. We are on the surface like this, standing here. Standing here. Please, this should not confuse you that the head of human beings is on the ground. They are standing straight as of here. I'm standing. Standing here. Some people are standing here. And no one. Now, here is the center of the Earth. Center of the Earth. So if you are here at this point A, another person is inside the valley here B, another person is on the surface of the Earth here C, another person is here D, A, B, C, D. The distance from here, each of these, to the surface of, to the center of the Earth vary. From here to here, the distance is different. From here to here, the distance is different. From here to this person staying here, the distance is different. And from here to somebody staying here, the distance is different. So if you measure that 1 kilogram at these different points, you will get different values. But the variation will be too small. the more something is closer to the center of the earth, the more matter is closer to the center of the earth, the more they pull. On top of earth, on the surface of the earth here, if you measure here, if you weigh something, that's 1 kilogram. If you measure it inside somebody who is exactly on the surface here, you get 9.81 Newton. Somebody that is here, I measure that same here. We will not get exactly 9.81. You get something like 9.79 Newton. So different points or different locations gives us different 9.8, 9.2, and so on. So what I try to say that the weight will be less than the weight gotten at the value A. Somebody here will get lesser weight than somebody here. The more it is, the more the matter is closer to the center of the earth, the more the value of the weight. So different weights implies different what? Masses. That is very clear. Now let us look at some calculations. Let us look at some calculations. Example 1. A rock is of mass 27 kg. Find its weight. A. On earth. B. On the moon. C. On the Mars. Solution. Remember this formula, W equals mg. Now, on Earth, the weight on Earth is equal to the mass, which is what? 27 times g, which is 9.8. If you multiply it, you get something like 264.6 Newton. Information, please. G, as I said, is 9.8. The unit is meter per second squared. Please forget about this squared for now. Let it not confuse you. We come to know how this squared came about. Now we have calculated this weight. Now we have got it to be 264.6 Newton. Newton M is in honor of a great scientist called Isaac Newton. To honor Isaac Newton. Isaac Newton. That's why this is L. Now, let's continue. If you are in the moon, what should be the weight? Using the same formula, W is equal to mg. On the moon, the same matter, mass, 27 kg, was taken to the moon, 27. Multiply that by g in the moon. G in the moon is what? 1.62 meters per second squared. So this, if you multiply, this will give you what? 43.74 Newton, and so on and so forth. That's the C1 can be done on the mass. Just follow the same method. Now, Now let's look at another example. Example 2. Example 2. The weight of certain scraps of metal is 40,000 Newton. A certain scrap of metal has a weight of 40,000 Newton. What is the mass? What is the mass? Solution. Certain scraps of metal was weight, and this is what it gave. So you bring the formula, W is equal to mg. The formula, W is equal to mg. Now, we are told that the weight is 40,000 Newton. And we are using what is the mass? Take G. We are told to say take G. At times, we are told, for convenience sake, we are told to take G to be 10.10 meter per second squared. You know that G on Earth is 9.8 meters per second squared. But at times, we are approximated to G equal to 10. So this question, we are told to take G equal to 10 meters per second squared. Now you substitute. The scrap has a weight of 10 Newton. 10 Newton, once you see this thing, Newton is telling you that it's weight it's talking about. So that's what we get, that was guide. When you see certain machines that are designed to carry out weights, as this one I'm showing you here, this one I say here. Look at inside the calibration. Is it calibrated? Is it what I say? Is it kg? Or what? N. If you see N here, okay, beside this round aspect. If you see kg, it's telling you that this is measuring in mass. Mass is measuring. If you see N, it's measuring in what? What is measuring in what? Weight. So now let's look at this. What is the mass? We know since the weight is 40 Newton, W is 40,000 Newton, equal to the mass M times G. Based on this formula, G is what? We are supposed to take G as 10. Therefore, let's get the value of M. You can type this is the same thing as what? 10M equal to what? 40,000. 40,000. Now divide both sides. Divide both sides by 10. Use my algebra. Divide both sides by 10. That is 10M. You divide by 10. 40,000 divided by 10. 10 cancels 10. We're left with M is equal to what? 4,000 kilograms. Now, this is the two examples we are going to take here for now. So, this is how we explain mass and weight. Now, in summary, take note, in summary, mass is a measure of how much matter is inside an object. How much matter? The billions of particles which come together, hold themselves together to form billions of atoms. Those billions of atoms hold themselves together to form the what matter you're talking about. It may be this, maybe metal, maybe another matter. Mass is measured in kg, very important also. Mass is the same anywhere, regardless of the object's location. That's that. Weight. Weight is a measure of the force of gravity on an object, the pull that drags something. If I hold this thing, I'm holding on this thing now, and leave it, the earth will drag it to itself. It's trying to get to the center of the earth, but it's stopped by this table and the earth crust. It's trying to go to the center of the earth, they cannot get there. Weight is measured in Newton. In honor, Newton, capital is N. in honor of a great scientist called Isaac Newton, one of the father of classical physics. Weight can change. Third one, weight can change depending on how much gravity is acting upon an object and depending on the location. Note, relationship. Mass and weight are proportional to each other. The more the mass, the more the weight. The more the weight, the more the mass. You should also know that mass and weight are often confused. With this lesson, we come to the end of today's lesson. Till some other time. Thank you.